Hello friends, Namaste and Jai Hind. Welcome to my show Engineering and Technology Made Simple. In today's lecture of mathematical models, we shall see the concept of Taylor series, its physical interpretation and couple of simple application. Basically, what is a Taylor series? Taylor series is a power series which is used to express any arbitrary mathematical function such as e raised to x, sin x, cosine x in terms of powers of variable where the coefficients are given by derivative of the function. Now consider a simple form of Taylor series in one dimension given as f of x is equal to f of a plus f1a into x minus a plus f2a into x minus a whole square, plus it can go up to infinity with an intermediate generic term as fna into x minus a raised to n. If you observe this Taylor series and for the time being, if you replace f of a by 1, then you'll get the terms 1 plus x minus a plus x minus a square plus x minus a cube and so on, which can go up to infinity with the intermediate term of x minus a raised to n. So basically it is a power series in terms of x minus a, where a is an arbitrary point near x about which entire series is expressed in terms of powers of x minus a. When we see the complete series, the coefficient of each component is given by function and its derivative at point a, and therefore we will find the complete equation of a Taylor series. So remembering Taylor series is not a very difficult step or process. It is a just power series in terms of x minus a, where a is an arbitrary point around x and the coefficient of each term is given by the corresponding order of derivative. That is a first order term x minus a, there is a corresponding coefficient with a derivative of first order and so on. Now this expression can be expressed in a compact form as f of x is equal to summation n is varying from 0 to infinity fn a into x minus a raised to n. Now this expression or series can be expressed in another form which is typically used in various applications, in which we can replace x minus a by h, and we'll get another form of Taylor series where x will get replaced by a plus h. So f of a plus h is equal to f of a plus f1a into h plus f2a into h square and so on, with a generic n term as fna into h raised to n, and it will continue up to infinity. Typically this is a very useful expression which is used to solve many problems in adaptive signal processing, Kalman filtering and various other applications. This equation can be similarly expressed in a compact form using summation sign, same as a previous equation, that is f of a plus h is equal to summation n is varying from 0 to infinity of fna into h raised to n. So it's a very simple expression, though initially Taylor series sounds intimidating. Now Taylor series can be extended to a vector variable as well as vector function. For example, f of x is a vector function of vector variable, so where x can be a vector having n components, x1, x2 up to xn. Vector we already discussed in our previous lecture. Now one can express a function also as a vector function, that is a function has m components as shown as a row vector f1x, f2x, and which can go up to fmx. So it has a m components. Now here both function and variables are vectors, and such type of functions or variables are typically used in computer vision and artificial intelligence subjects. Now here, this is a very important matrix which is called Jacobian matrix, and then all the three concepts of vectors are combined here, and these concepts are derivative of vector function, and derivative operator itself as a vector, which we had seen in our previous lecture. So here, when vector differential operator operates on vector function with a vector variable, it can be expressed as a Jacobian matrix, where Jacobian matrix is given by a row vector as shown below, dabba of f of x1 with respect to dabba x1, dabba f of x2 with respect to dabba x2, dabba of fxn with respect to dabba xn. Now here, though it looks like a row vector, if you observe each term in this row vector, it is a derivative of a vector function. So where f has m components f1 to fm. So each term in this row vector is expressed as a column of m function, and therefore it will form a matrix which is called Jacobian matrix. Now Taylor series in n dimension is an extension of one dimension equation, where one can easily map by assuming x as a vector, which is shown below. It has n components, x1, x2 up to xn. Now the series expansion becomes slightly difficult due to the matrix representation, because vectors are nothing but the column matrix or row matrix. But once we become habitual to visualize vector as a matrix, then this expression is not as difficult as it seems. So here it is expressed as f of x is equal to f of a plus x minus a transpose into gradient of f of a plus 1 by 2 factorial into x minus a transpose into H matrix multiplied by f of a into x minus a, where H is called Hessian matrix, and your variable x has n components, which is expressed as a column vector, and gradient of f of x is basically nth order derivative, which we already discussed in our previous lecture. Now the Hessian matrix is a second order matrix which is given by d2f by dxi into dxj. So this is a second order matrix, and one can imagine the Hessian operator as a h which operates on a function, and that is computed as a second order matrix. One can express Hessian matrix in terms of Jacobian of gradient of f of x. So we are not going in details of or proof of this equation at this point of time. Now similarly, this expression can be expressed another form of a representation, that is f of x plus h is equal to f of x plus h transpose gradient of f of a plus 1 by 2 factorial into h transpose into Hessian matrix of f of a into h. So this is the same concept we applied in one dimension. Now we'll see what are the simple application of Taylor series. So one of the important application with respect to artificial intelligence is a back propagation algorithm, where the weights are updated in a feedback loop of training algorithm. Now, how one can update the weights in any adaptive filter or a neural network or a deep learning models, as w of n plus 1, that is the weights in the next iteration, is equal to the weights in the current iteration w of n incremented by a very small value, that is a delta w. So this is a very standard idea of updating weights in any adaptive algorithm. Now what is the criteria for the choice of delta w? Obviously one can see the choice is error, which is expressed as a epsilon in your adaptive processing algorithm, should be smaller in current iteration compared to the previous iteration, where in current iteration weights are updated by factor delta w. Whenever w is updated by delta w, the expected error should be lesser than the previous value, or bare minimum it should be equal to previous error value, and therefore you'll come across the equation epsilon of W plus delta W is less than or equal to epsilon W. Now here, this problem can be solved using a Taylor series as follows. Now we can expand epsilon W plus delta W using a Taylor series, where we'll consider only first two terms, because delta W, we already assume it is very, very small, and hence one can ignore second order and higher order terms. If you compare with the equation f of a plus h, then your W is mapped to A, while increment h is mapped to delta W. Now you can expand this equation as a epsilon W plus delta W into DABA of error function with respect to W less than or equal to epsilon W. Now here, how one can assure the left hand side term is less than or equal to right hand side epsilon W, which is a error in previous iteration. The only choice available is delta W has to be chosen as minus of mu into partial derivative of epsilon W with respect to W. Now what will happen with the help of this choice is, in previous equation, DABA epsilon of with respect to DABA W will become square, and it will be always positive, and therefore a constant mu with a negative sign will ensure entire term will become negative, and hence the overall quantity of error in iteration n plus 1 is always less than or equal to error in iteration n. So this is a way incremental delta W is estimated, and then when it is substituted, weights are updated using the formula Wn plus 1 is equal to Wn plus delta W. This algorithm is called Wiedrohoff LMS algorithm, which is used in updating any adaptive filter or training algorithm, which is used in neural network or machine learning models or training of deep learning models as a back propagation algorithm. So this forms basically a foundation algorithm. Now there are various flavors of these algorithm, which are called gradient descent algorithm, stochastic gradient descent algorithm, adaptive gradient descent algorithm, RMS prop, and ADAM. However, the foundation algorithm of updating the weights remain same. There is one more application of Taylor series, which is used in Kalman filtering, and Kalman filter is used in tracking of the objects. Another important application of Taylor series is whenever hardware accelerator for mathematical function is implemented for e raised to x, sin x, all trigonometric functions, they are calculated using Taylor series. So these are the various interpretation of Taylor series in one dimension form, n dimension form, and some simple application of Taylor series. I hope you must have enjoyed this lecture, and thank you for your patience and watching my show.